if you run with different initial conditions, right?
Mm-hmm.
Then wouldn't your variation of ut be different for each case? So how can you compare that with the time average for a single initial condition?
If you perform an ensemble averaging, you would be starting from, you have u1, u2, etc., right? And each one is a function of space and time. And what the ergodicity assumption implies is that when you take t to be large enough, okay, as long as t is large enough, the average 1 over n times summation of ui, I goes from 1 to n, as the limit of n goes to infinity, is the same no matter what t you choose. Okay, so this averaging says that this time average is the same no matter what initial condition you choose. This ensemble average is independent of what time you choose, as long as the time is late enough.
But the averaging is done based on time, right? Not spatially.
This averaging is done based on initial conditions. It's averaging across different initial conditions, an infinite collection of initial conditions. All right. Does it make sense?
Yeah, I'm still a bit like when you do that time average, right?
Mm-hmm.
In the end, your average u is still a function of x, y, z, right? Like spatially.
Yes.
So it's the same with the ensemble average as well.
Yes. The resulting is a function of x, y, z. Yes. Okay. So x and t, right? So this is saying that if you average this will be x and t, but this is a steady state flow field, which means the big U is independent of t now. And here, it's pretty clear that the resulting U is just a function of x and independent of t.
So if n goes to infinity in the bottom equation, the big U will also be a function of x. Only.
It will also be a function of x.
Only.
That's right. That's right.
T.
Right. It's a for finite t, it's only a function. It's a function of x and t. But as t goes to infinity, this big U would converge to some steady state. Right.
Even if you set like all sorts of ridiculous initial, like you can, there's no limit to what you can set as your initial condition.
There is a limit. It has to be non-singular, right? So in the mathematical sense, it means the initial condition have to have a density, and the density has to be a function. It cannot be like delta function. That makes sense. Okay. And okay. Any other questions about this? I know it's a concept harder to understand. If you would like, I can show you a case of what does it mean by these ensemble averaging approaches, time averaging in something other than fluid dynamics, in some other chaotic dynamics model like the Lorentz model. I can show you. Can go to YouTube and so let me show you that.
Need a bigger washer? We guarantee the lowest prices on all appliances.
Okay, so here is a ensemble. So if you look at the white dot over here, it's actually not a single simulation, but an ensemble of many millions of solutions. And this is the phase space. This is a three-dimensional phase space projected into a two-dimensional screen. Okay, so in this case is not a PD, but a 3-degree of freedom ODE. And the ensemble is a collection of initial conditions within a very small ball. So this keeps evolving, and because of the instability of the governing equation, even if you start from a very similar initial conditions, a tightly packed collection of initial conditions, after a while these solutions become more and more different. It's just like if you do a fluid dynamics experiment in the lab, even if you try to control the initial condition and the environment as well as you can, once you start the experiment, you see, if you conduct experiments twice, you see these experiments will soon break down. It will no longer be exactly the same after a short while. This is like the same sensitivity of initial condition in any chaotic dynamical system. But once you perform such experiments, the statistics of the flow should not be sensitive to either the initial condition or small variations in temperature or humidity or things like that. Right, so this is showing that after a long time, these many millions of ensembles, they spread across the phase space. And this butterfly-shaped feature is this ensemble, is what this ensemble is. If you take an average across all these points, the average is somewhere here. That's the average. Then after a long enough time, it doesn't move anymore, right? Even though the ensemble is still, every point on the ensemble is moving. If you take the average, it'll be here, won't move anymore. Okay, and this ensemble average will be the same as averaging just over a single trajectory, but over a long time. So this is what ergodicity means. Yeah, in this case, I can either take the spatial average or take the long time average. It doesn't matter. But this is a very cheap equation to simulate. It's just the 3 ODEs, and I can afford to simulate it for several millions of times. But if I have a turbulent flow field, nobody has the computing power to simulate it for several million times. So taking a time average is usually the more economical thing to do.
Can you prove ergodicity?
You can prove ergodicity for equations like this, but nobody even proved that the solution exists for a Navier-Stokes equation, not to say ergodicity.
So it's just an assumption that we make.
That's right. It's an assumption we make, and it seems a lot of experiments validate that, even though there are cases where ergodicity is violated. So for example, there are boundary conditions where you can observe hysteresis in fluid dynamics, where if you start the flow from different initial conditions, it'll converge to a different statistical steady state, right? And a very easy case to think about is the start of a wind tunnel, like a supersonic wind tunnel. It can be on 2 states. One state is the test section is choked, which means it's subsonic. But if you start it with enough pressure, it'll be supersonic. So these are there are cases where you don't have ergodicity, but in many cases we do. Okay, and the Reynolds averaging assumes you do have ergodicity in some extent.
So shocks are a case where you wouldn't.
Why?
Like for well, like you said, for supersonic flow, isn't like how? I guess after, like, if something is choked, right?
Yeah.
After that, if you keep increasing an initial condition, like say pressure, you can't really affect the flow downstream, right?
If something is choked, if you increase that's when you change the boundary condition, you don't affect things downstream.
So wouldn't that be an example of non-ergodicity?
Non-ergodicity means that if you change a different initial condition, you would get something different. So for example, one of non-ergodic cases when you have a scramjet. Let's say this is this is a two-dimensional cross-section of what can be a scramjet design. And so the design is such that the air is compressed when it goes into the inlet. You get a chain of oblique shocks, and that compresses the air, and you inject fuel. It burns here, creating a higher stagnation pressure and stagnation temperature, and afterwards you expand the flow to create thrust. So, but one of the failure scenario is that you have too much heat release and the whole thing, and that therefore you develop a normal shock here. So one of the failure cases is that the whole thing is going to choke. So you get a bow shock out of here, and the whole combustion chamber becomes subsonic. And there is going to be a region where you just have enough heat release so that you have a bistable state. Right? If you start from a solution that is choked, you will remain choked. If you start from a solution that is supersonic, you will remain supersonic. So that's one of the cases where the flow is not ergodic.